Okay, folks, uncompetitive inhibitors are next. So this type of inhibitor is different from a competitive inhibitor, that it will only bind the enzyme in the enzyme substrate complex. So the enzyme must first bind the substrate before it will bind the inhibitor. This type of inhibitor, generally will not bind the enzyme. When it's just the enzyme, we need that enzyme substrate complex. And what's happening is that the inhibitor distorts the shape of the enzyme active site, and we'll see how that impacts the Livezey plot in a moment. So how can we recognize an uncompetitive inhibitor from a Livezey plot? Well, take a look at this. All the lines are parallel to one another. So when you see a plot like this, no, uncompetitive. But what we're seeing here, as we add increasing inhibitor, we see that the Km is shifting to a larger -1/Km, so Km appears to be decreasing. And we see that Vmax must be decreasing since 1/Vmax is increasing. Why would it make sense for an uncompetitive inhibitor to make Km smaller and Vmax smaller as well? Let's draw it out, folks. So here in the scenario, we have our good old enzyme and substrate and inhibitor. But what needs to happen first is that enzyme needs to bind its substrate. But once this enzyme binds its substrate, and actually I should have drawn this a bit more carefully, so let's try this one more time with my enzyme. Once that enzyme binds its substrate, there is now a location for this inhibitor to come bind. Okay, let's recap what I just drew. We had our enzyme and our substrate and our inhibitor. Once the enzyme binds substrate, then the inhibitor is able to bind. We saw that both Km and Vmax were appearing decreased. So let's look at what I drew to try to understand. So Km appears to be decreased, which means that the enzyme is binding substrate better. But if you look at what I drew, you'll see that when the enzyme bound its inhibitor, the shape of the active site changed. And it changed in such a way that the substrate seems kind of like locked in or trapped into that active site. So it makes sense for Km to seem like it's getting better if that substrate's kind of locked in there. However, folks, we saw that Vmax also decreases, which means the chemistry is getting not better, but worse. And why would the chemistry be getting worse? Well, if we changed the shape of the active site, we most likely changed the shape of the catalytic site. See how I'm not a great drawer here, folks. See how in the drawing with just the enzyme and the substrate, I tried to draw this like perfect matching up of the enzyme to the substrate. But once the inhibitor's there, we have this like gap that I tried to draw in there. Please forgive me, I'm not an artist. Well, what's happening is when we change the shape of the catalytic site, the catalytic residues aren't in the proper alignment anymore. So the chemistry happens worse. Whenever we change the shape of the active site with an inhibitor, it's going to be worse for the chemistry because the arrangement of the catalytic residues is no longer ideal. So Vmax decreases because shape change of active site leads to a shape change of the catalytic site. And poor chemistry. Because those catalytic residues are all weird. Last up, mixed inhibition. And so I like to describe this type of inhibition as mixed because I think this is a much better descriptor for the type of inhibition it is. Mixed inhibitors are kind of a little bit competitive and a little bit uncompetitive. The inhibitor can bind to the enzyme and the enzyme substrate complex, right? So we can bind substrate, and we could bind inhibitor just to enzyme, or we can bind inhibitor to enzyme substrate complex. How do we recognize the graph? So in mixed inhibition, we're going to see an intersection of the lines within a quadrant. So it's within a quadrant. Oops, didn't mean to say quadrants. As we add inhibitor, folks, Km can either increase or decrease. And this is going to depend on, maybe if that line was a little bit better drawn, huh? This depends on if the inhibitor is more competitive in nature or more uncompetitive in nature. So a mixed inhibitor will be both, but they tend to have a slight preference. A little more binding to just the enzyme or a little bit more binding to the enzyme substrate complex. No matter what, Vmax appears decreased. So let's go ahead, draw this scenario, and try to understand what's going on with a mixed inhibitor. So again, say, Dr. Livezey, be a little bit more careful. I'm gonna do my best. It's hard not being an artist and having to draw so much. Okay, folks, in this case, here's our enzyme. Here's our substrate. Here is our inhibitor. And so what can happen is that the enzyme can bind inhibitor, first. It can bind substrate first. So in the kind of top scenario here, folks, you can see that this inhibitor is slightly more competitive in nature in that the inhibitor is going to bind the enzyme instead of substrate. But you see in this mixed inhibitor, it's not competing by binding to the active site. It's competing because when it binds to the enzyme, the shape of the active site changes, therefore blocking the substrate. Now, if we compare that to if the mixed inhibitor were slightly more uncompetitive, you see the inhibitor wouldn't bind the enzyme until substrate was already bound, and so in this case the substrate would be kind of locked into the active site rather than locked out of the active site. In both cases, so let's start with Vmax. In both cases, Vmax decreases because the shape of the active site changes. And if the shape of the active site changes, the shape of the catalytic site changes. And if the catalytic residues are now in different locations, the chemistry is worse. It's got to be worse. If we're changing the shape, it's no good. Now, Km will either increase or decrease. The Km will increase if it is more competitive than uncompetitive, or Km will decrease if it's more uncompetitive than competitive. So Km increases if we see inhibitor binding more just enzyme and kind of blocking the substrate from like ever getting in there, right? Km is going to appear to decrease if we have enzyme substrate already bound and then the inhibitor comes in and so it locks it in there. Keep in mind, folks, that mixed inhibitors are doing both of these things. They can do both, but they will generally tend to have a preference one way or the other, just depending on, can the inhibitor bind better to the enzyme like this or like this. The last thing I'll mention before letting everyone go is a subtype of mixed inhibition that is like inactivation. So remember, inactivation of an enzyme is when we kind of injure or kill the enzyme's activity. Inactivators from their plot look to be what's called a pure non-competitive inhibitor. So you can see what's happening in this graph is we have an intersection on the x-intercept. So we have no change in Km, but the Vmax is getting worse and worse. And we're not going to focus on this in this class, folks, but just know for other classes that this is happening because they are literally killing the enzyme. Either they bind really tightly and it's hard for the enzyme to dissociate to go do its thing, or they bind covalently and so in effect destroy the enzyme.